Okay, welcome back and greetings, my fellow engineers. In this video, we're going to talk about a software-driven approach in which we can address that load word data hazard from the previous video. Okay, so in the previous video, we looked at the issue where we had a problem with the load instruction, and in particular, there is the issue that if we look here at this example, where a dependency comes up, right? If we have a load word or a load instruction that is writing to a register, in this case register 2, and the following subsequent instruction immediately after it is reading it. Okay, the problem that we would have to stall the pipeline. We'd have to stall the pipeline in terms of being able to forward that correctly, so that we don't run into an issue with not having the value available for in this case instruction 3. What we want to look at is, as I mentioned at the end of the last video, is stalling is not an ideal scenario, right? When we're talking about designing processors and computing systems, is performance is a major concern. We're trying to get a lot of work done in the shortest period of time possible. And stalling is not ideal. We're wasting some clock cycles, and we would prefer to avoid it if we can. And what we're going to see here is that the compiler can assist us. We can have compilers do some smart optimization to be able to reorder instructions in such a way as to eliminate some stalls. Maybe not all of them, but we can eliminate a certain number of them. So let's look at this example here. And if we look at the first part of this, and you can imagine this is just, whatever, pseudocode or C or Java code, where we have these two lines. We have b plus e that value is going to be written to some variable a, and b plus f is going to be written to some variable c, and we're going to assume all these variables are in memory, such that here we're going to basically get the value. We're going to get b from memory, so we're going to load it from memory and put it into a register. Okay, here we're going to get register variable e from memory. Okay, then we're going to add them together. Okay, we're going to do the b plus e. Okay, and then here we are storing that result right into the address that is going to be used to represent variable a. Okay, those are the first 4 lines, right? So notice that each variable is assigned a memory address. Okay, here, right, we've got this other load is our f, where we get value f out of memory. Okay, and we have another hazard, right, load hazard, in which the next instruction after that is doing our logic where we have b plus f. Okay, and then at the end here, this last line is our c equals b plus f. Okay, so these 7 lines, 7 ARM instructions handle the 2 lines above. Okay, and notice we've got, in this case, we have 2 stalls that occur. Right, we have 2 stalls that would have to occur because we've got these 2 dependencies happening where we have a load followed by an instruction that is reading the same register that the load is writing to. Okay. Now, ideally, right, we kind of look back at this. We want to ask the question, like, can we reorder this in such a way that we can avoid is there a way that we can look at, say, something like this and do it in a slightly different order, such that we avoid having to stall the pipeline? Okay, so if we look at this example here again, and remember, like, we've got these dependencies here, okay, and here, and the question kind of raising is there a way that the compiler, instead of generating, so the compiler, as we know, right, takes a higher level language, say C, and it compiles it into assembly language, say ARM, and compilers can do, in the real world, they do all sorts of smart, intelligent optimizations, okay? And what we want to do is say, like, think about what can the compiler do in a scenario like this to ideally avoid having to stall. So can we get some help? Can we have a software-driven approach that is going to make the running of this program faster without changing the functionality? That's a key thing. It cannot impact the result. It cannot impact what the logic of the program does. Okay, so we can't just change it any which way we want. It has to be the same functionality, right? And one thing that you might notice, and there's more than one way to get this to work, but one thing we could do is if we take this instruction here, oops, right, if we take that instruction there and we move it up, okay, and we do that right there, okay, if we do that right, we could do that in place of the stall, right? So we can actually move that instruction up so that we do those 3 loads in a row, and we'll see if we do that, we're going to get this, okay? Where on the left is the original. On the left, we've got these issues where we have to stall here and here, okay? But if we take that load and we move it up, okay, what we're going to see here is if you look on the right, there is no issue with having to stall, okay? By moving that instruction up earlier, we've completely eliminated having to stall the pipeline, okay? So that whole program is going to run 2 clock cycles faster because you're eliminating both stalls. Key thing about it is it doesn't impact the functionality at all, right? Because we had nowhere was register 4 used where we just happened to read that memory address earlier. We didn't impact anything in the program, right? Which is key thing. Like, we can't just move anything we want, right? We can't just move any instruction to avoid the stall. We have to be careful that we are not impacting the functionality, okay? And so this is a short video, just to kind of show you like one other example here, right? If we look at this example here, we could see that the same kind of idea, right? We've got a dependency here, and we could simply just do the load a little bit earlier, okay? And if we swap 2 instructions, this functionality is the same, right? The reason we can do that is this instruction here, right, is there's no dependency on the load happening earlier. So there's no dependency between these instructions that's going to cause something to operate differently. It's not going to cause something to break or to get a different value by moving those, okay? So you have to be careful when you're trying to reorder things to see what would happen. You have to be careful that there's no dependency that's going to cause a change in the functionality of the program when it's run, okay? All right. Sometimes, right, depending on the program, sometimes you're going to have to stall, right? Sometimes stalls are inevitable. Sometimes you're not going to be able to avoid it. Okay, so that was a pretty short video, but I think it gives you a nice different perspective on the fact that you can use a software-driven approach to increase performance. Gives you a sense of some things of what compilers are doing to try to optimize your program. All right, there's a lot of work over many years in terms of compiler design, and it's an important aspect in terms of making code run faster, right, without sacrificing or without relying on the hardware to either stall or do other types of functionality that can be solved or addressed by the compiler. Okay. All right, so I'm going to wrap up this video. We'll keep it nice and short and sweet, and that is going to wrap up our discussion of data hazards. And this is a good way of understanding how the pipeline works and how we're addressing some of these many problems that come up when the fact that we're using parallelism to be able to increase the throughput of our CPU designs. And like always, ask questions and stay safe and healthy.